Hello everyone, welcome to Practically. We bring learning alive. And today I have brought a chemistry comprehensive series for you, wherein we're gonna cover organic reaction mechanism. Such comprehensive series are there for physics and biology also. But since I'm a chemistry teacher, I'm gonna cover a chemistry comprehensive part wherein we're gonna see complete organic reaction mechanism, and we're gonna start with none other than SN2 reaction. We know what's the meaning of SN2, right? It's N2, substitution nucleophilic. 2 stands for biomolecular. Okay, so it's a second order reaction. And we know as far as stereochemistry is concerned, in this reaction there is an inversion. There is an inversion of a substrate when it reacts. So that inversion and other aspects we're gonna see graphically firstly. Okay, basically I have put an animation. So let's see what it is. So this is the CH3Cl, as you can see, okay, and that is a OH minus. What is that? That's an OH minus. It has brought a negative charge here. You can see here. This is a negative charge. Now, oxygen wants to attack the carbon. Why does it wants to attack the carbon? Because oxygen has a negative charge, carbon is having a delta plus, and chlorine is having delta minus. Why do you have that? It is because of electronegativity difference between them, right? Carbon is less electronegative than chlorine. That is why chlorine has a delta minus, carbon has a delta plus. And oxygen, obviously you can see oxygen is having a negative charge. So oxygen wants to attack the carbon. But the thing is that chlorine would not allow that. Why? Because chlorine is having 3 lone pairs around it. You can see here, these are the lone pairs. These are the lone pairs. Similarly, your oxygen is also having a lone pair. We know that oxygen has 2 lone pair and 1 negative charge. So this basically, even if you take a lone pair, even if you take a negative charge, those are nothing but what? Electrons. And we know that there is a repulsion. There is a repulsion between the electron. There is a repulsion between the positive charges. We know that. So because of this repulsion, chlorine would not allow oxygen to attack. Let's see. See, now they are fighting, right? So now here they are fighting with each other. See, now oxygen is kind of a scared because of chlorine. It would say, I don't want to attack from this side because chlorine is not allowing me to do so. So yeah, moving ahead. Just this. Yeah. Yeah. So oxygen thinks, see, what I have shown here is that oxygen has a thinking of attacking from the backside. Okay. So now oxygen wants to attack, as you know. See, so oxygen goes there and here it comes. It comes on this side, and that is how you have a backside attack, right? You have a backside attack. So this is how your oxygen wants to attack the carbon. See what is happening here? This is a stereochemical. Let me show you again. Let's go back. So oxygen thinks of attacking in this way, but as we had seen, chlorine is not allowing oxygen to attack. So oxygen just flies from there. It comes here to the back side of your carbon. From there, it tries to attack in this way. And as soon as it attacks, or as soon as it starts to attack the carbon, the stereochemistry starts inverting. See, it has started inverting already. Now, see, the bond has started breaking now. Which bond? The carbon-chlorine bond has started breaking now. Now, I will come to this later on, that how this bond breaks, what is the transition state and all that. Here, I'm just going to give you a brief insight. So, bond has started breaking. Now, the bond has formed completely, and now chlorine will fire. That is how the stereochemistry, you can see, previously we started with stereochemistry just like this. this was your stereochemistry. Okay, this was chlorine. So if there was no inversion, it has to give you a compound which should look like this. But what it gave you? It gave you this OH, C, CH, CH, CH. So what has happened basically here? What has happened here is a inversion of configuration. What is mean by inversion? That we will understand as we move ahead. Okay, sure. Moving ahead now. See here. Now SN2. What kind of substrate where SN2 reaction actually happens? Okay, there are different types. The first type that we just saw was actually this, where you have this was your substrate and this was your substrate and this was your nucleophile. That is the first type where we saw that substrate is neutral whereas nucleophile is charged. Second, you have a substrate is neutral again and your nucleophile is also neutral, but nucleophile is having what? Your nucleophile is having negative charge. Your nucleophile is having negative charge. That's the difference. That's the second type of SN2 reaction. Then we have a third type of SN2 reaction. What is that? Where you have your substrate neutral. Your substrate is neutral. Sorry, my bad. You have a positive charge here. Just a sec. Yeah, you can see here. The third type is your substrate is having positive charge and your nucleophile, upcoming or incoming nucleophile, is having negative charge. That's the third type. And the fourth type of reaction is that where your substrate again is positively charged, but the nucleophile is neutral. So it is very simple. There are two types of substrate only. One substrate is neutral, another substrate is positively charged. So the neutral substrate would be reacting with charged nucleophile, neutral nucleophile. Those are two types. Then the charged substrate would be reacting with charged nucleophile and neutral nucleophile. That is how you have four types of reactions. Okay. So moving ahead with this. Now you can see here, this is your nucleophile, right? This is your nucleophile. Now this nucleophile is attacking your carbon. Now what is the hybridization of your carbon here? The hybridization of your carbon here is sp3. You can see here, hybridization here is sp3. Okay, let me change the color, otherwise you would see in a better way then. Yes, see, this is sp3. Okay, it is a sp3 hybridized carbon. As soon as your nucleophile start attacking, your carbon, what is happening is that, see, this is your transition state. This is your transition state. Now what has happened in this transition state? See, this Y started depositing. This Y started depositing electron density into the anti-bonding orbital of CX bond. See, earlier there was a CX bond. Okay, every bond has, we had seen in MOT that every bond has two types of orbital: bonding molecular orbital, anti-bonding molecular orbital. So whenever electron goes into the bonding molecular orbital, the bond strengthens. Whenever electrons are getting deposited into anti-bonding molecular orbital, the bond started weakening. So what is started happening here is that Y started forming a bond with your carbon. Okay. Now there is a deposition of electron density into the bonding orbital of Y and C bond. Okay. But at the same time, there is also a deposition of electron density into the anti-bonding orbital of C and X bond. That is why slowly the bond between C and Y starts forming, and with the same rate, the bond between C and X also starts breaking. So basically, suppose if you say initially Y has formed a 10% of bond with the C, then at the same time 10% of bond must have been broken with the X. So as this process moves ahead, slowly, Y now has formed a 50% bond with the carbon, and X has broken a 50% bond with the carbon. As this moves ahead, when you go to the 90% of the bond formation between Y and carbon, then the 90% bond has been broken between carbon and X. Now, how does this bond breaks between carbon and X? As I told you, the one way of viewing this is that there is a deposition of electron density into the anti-bonding orbital of CX, and the second way is that, see, every bond breaking process, you take any kind of bond, this bond breaking process is always what? It's endothermic, isn't it? Every bond breaking process is endothermic. So here, whenever this reaction was happening, you need to provide the energy. So where do you get the energy from? Let me tell you that. See, whenever the bond formation is an endothermic process, at the same time, the opposite of that is bond formation. If the bond breaking is endothermic, bond formation has to be exothermic, and it is exothermic. So here, as the bond was started forming between Y and carbon, slowly, I know that bond was forming slowly, but with that slow speed, the energy was getting evolved, and that energy was then utilized for the formation of the bond between carbon and that energy was utilized for the breaking of the bond between C and X. Basically, C and Y formed the bond slowly. Whatever portion of the bond which was formed, that has released some energy. Now that released energy now is utilized to break the bond between carbon and X. So that is how it was actually happening. So the one you are seeing is transition state. And you can see here, carbon neither have a strong bond or complete bond with Y, nor it has a complete bond with the X. That means these two are not complete bonds. The complete bonds are only three: 1, 2, and 3. And we know that carbon do not have any lone pair. So how do you find the hybridization of this state now? As I told you, hybridization here was sp3. So here carbon has formed only 3 bonds. Other 2 are partially broken and partially formed bonds, and there is no lone pair on the carbon, right? So 3 number suggests what? It suggests that hybridization is sp2, and it is sp2. Okay, it is sp2. You can see here, this is a trigonal shape, trigonal planar shape. Okay, that is why you have this transition from sp3 to sp2 and again back to sp3. Now the nucleophile X, this X now becomes your Lg. What is this Lg? Lg is your leaving group. Okay, see now. So whatever I have written, I hope you must have understood it. sp3, sp2, again sp3. Okay, now let me show you one more thing here. See, now I'm going to tell you the stereochemistry. This, see, what is mean by inversion? You can see here inversion completely. You can see here the inversion. See, this carbon was like this. This must be your hydrogen, right? Hydrogen, 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 or whatever it is. In this case, we are considering it as a hydrogen. This was your X. Okay, your Y minus came, attacked on carbon, then X depart, Y stays there. Now Y has basically formed a bond from the back side. This Y has formed a bond from the back side, which has inverted the stereochemistry completely, right? So now let's see how stereochemistry works here. See, this was your umbrella first. Now the bond formation has started. See, it has completely reversed the umbrella, and now the inversion. See, this was your carbon first. Now it has happened what? It was like this. Now it is like this. It was like this initially. Okay. Now it became like this. What is that? That is called as inversion. That is called as inversion. You can see clearly. The umbrella has inverted completely. Now it has upside down. Upside down is what? It's a inversion. That is what happens in SN2. Let me show you once again. See, this is your substrate. Now reaction started. Now this is in the midway, somewhere midway between the starting substrate and the product. So that goes, and you get what? You get the inverted configuration. Okay, that is how the inversion actually happens. So this is how inversion happens in every SN2 substrate. But for you to check out whether inversion has happened really or not, you need a what? You need an optically active substrate. Then and then only you can identify it. Okay, sure. Moving ahead. Now again the transition state, as I told you, it is started with sp3, right? And where it goes into the medium state, it goes to the sp2. So same thing is there. Only thing is that this time I have brought a reactant. I have not put this sample. I have not put a sample here. For example, C and bonds. I have put C, hydrogen, OH minus is attacking on your carbon. Here it's a transition state, and we know that oxygen is having a delta minus on it, Br minus is having a delta minus on it, carbon is having a delta plus on it. Basically you are having delta plus minus, you can say both, but to be precise, you are having a negative charge here. Okay, or you can say the transition state is charged. Transition state is charged for SN2 reaction. Okay, and lastly, you have already seen how the stereochemistry plays its role to show the inversion of configuration. Okay, chalo, moving ahead now. So what is the next? Next is SN2 reaction, but with retention of configuration. Now let's understand this point very, very clearly. Now there is a SN2. Now there is an SN2 reaction, but this time the configuration is not getting inverted. It's an retention. It's a retention. How come? Let me tell you. See, firstly, you know that whenever the SN2 reaction happens, what actually happens is that nucleophile attacks from the backside. So as soon as it attacks from the backside, obviously it cannot attack from the front side, so it is attacking from the backside. So when it attacks from the backside, obviously the whole inversion happened. I mean, every group gets mirror imaged to its original position, because of which you get the inverted configuration. But what if I tell you in neighboring group participation, it is also called as NGP is a shortcut, neighboring group participation. It is also called as anchimeric assistance. It is also called as anchimeric assistance. Okay, but anyway, we don't want to get into the name of it. What is it? It's anchimeric assistance. Okay, but let me tell you first, let's understand this to the graphics first. So this is your first substrate. As you can see, the umbrella there. Now what has happened? Reaction has started happening. See, the inversion has already happened here. Okay, I'll move completely so that you can see this. Now next, the same umbrella which was there, which was inverted, is now here. Now this umbrella will undergoing one more SN2 reaction, and you are getting what? See, this first umbrella and second umbrella, they are one and the same. They are one and the same. That means what? There is an retention of configuration. Why there was a retention? You need to understand that point. Okay. Now let me go back so that these umbrellas won't be there. Now you can see here this Z. See, this is your X. Now this X is leaving now. This X is your LG. LG means what? LG means it's a leaving group. Okay. Now whatever Z was there, Z is already present in your substrate. So it is attacking on your carbon from the back side. You can see here, as soon as it attacks, it forms a three-member transition state, or you can say a ring transition state. Okay, as soon as it attacks, X minus departs. So first SN1 has, first SN2 has already happened. The first SN2 reaction has already happened. Okay, now you got this. This is, you can call this a transition state or whatever. Okay, now your nucleophile comes. Now this is your nucleophile. The one we saw in the first slide, no, that nucleophile now comes. Now it also attacks from the back side. Back side of what? Back side of your Z. So it attacks from the back side, and again Z stays there where it was, but Y come into the place where X was. Here was your X, now here is your Y. So do you observe one thing here? There are two SN2 reaction here. So as I told you, one SN2 reaction causes inversion and two SN2 reaction would cause what? They cause retention. How? See, you started with this. Okay, so when you started with this, that was the first SN2, happened by what? Neighboring group. What neighboring group? Z was your neighboring group. So it gave you this first inversion. Okay, now your Z is still there. Now your nucleophile comes, and what does it do? Your Z is here now. It attacks, sorry, your Z is here. Here your nucleophile comes and attacks. It attacks, again it becomes like this. So what has happened overall? If you see in an overall, the overall there is a retention, because first reaction causes inversion, second reaction also causes inversion, but inversion of inversion is what? Inversion of inversion is retention. Just like in Hindi, ulte ka ulta, क्या होता है? सीधा, right? That is how neighboring group participation shows retention of configuration. So we'll see it once again. See, there's a retention now. Retention. Okay, chalo. Moving ahead. Now, kinetics. Kinetics is what? Kinetics basically tells you what are the substrates, or I would say what are the species on which the rate of reaction is dependent on. Kinetics tells you what are the substrates on which reaction is dependent on. Okay, and kinetics also gives you an idea how fast or how slow your reaction would be. Okay, but that I'm not going to discuss here, since that's a part of a chapter called kinetics. Here we are only going to see what are the substrates on which your rate of reaction is dependent on. Okay, so as you can see, the rate of reaction is dependent on oh, just a second. What color shall I? Okay, rate of reaction is dependent on substrate as well as nucleophile. So this is one, this is another, and what has become 1 plus one plus 1. What has it become? It's a second order kinetics. It's a second order reaction. Okay, as you can see, it's a second order. I have written here also. Now the question is why it's a second order reaction. So you need to understand that, see, SN2 reaction happens in a single go. Okay, there are two mechanisms here, SN2 and SN1. Okay, SN1 happens in a two processes, whereas SN2 happens in a single processes. Okay, there's only single process here. It is also called as the concerted process. It is also called as concerted process. Concerted process means what? Simultaneous process. Basically, it's a simultaneous process. Okay, now you need to understand that rate of the reaction is decided by those species which are present in the slowest step of the reaction. What is that? Let me show you again. So we started with this CH3. This was your X, right? And what comes is nucleophile. Your nucleophile comes, it attacks, right? As soon as it attacks, your X does not departs immediately. However, I am going to show that in arrow, but this process happens gradually. So basically there are two steps here also. Okay, in book you might see they have written that it's a concerted process, simultaneous process, or single step process. I know, but if you divide it at a micro level, you will see there are two processes or two steps. This is the first step. This is the first step, which is a slow step. First step is a slow step. What does it gives you? It gives you this transition state. Okay, that's the first step. Now you have a second step. Second step is a fast step. Have I written anything wrong? Yes, it is a wrong thing. Just a sec. Oh, what has happened here? Just a sec. Yeah. So let's rub it down. Yeah. So basically what has happened here is that now your nucleophile has come here and you get CH3 plus your X minus has departed. Okay, we know this. The first step is slow step, second step is a fast step. And as I told you, that whatever number of species you have, if they are present in a slow step of the mechanism, they will decide the rate of the reaction. And as you can see here, the nucleophile as well as substrate both are present in a slower step of the mechanism, or I would rather say the step that leads to the transition state, of the reaction. The number of species present in that step would decide the rate of the reaction. Okay, we will see how does it goes in SN1, but as far as SN2 goes, you can see here substrate nucleophile both are present, so therefore both will decide the rate of the reaction, and hence it's a SN2. Substitution nucleophilic bimolecular, right? It's a second order reaction. I hope this must have helped you understand how it is SN2. Okay, chalo, moving ahead. Now, effect of solvent. Okay, now that you have understood what SN2 is, how the substrate and nucleophile plays a role, how different kind of substrates are there. Okay, now let's see this reaction. You can see here the Ki is there. Ki gives you what? Ki gives you K plus and iodine minus. Your iodine minus is attacking on the carbon, bromine departs, you get ethyl iodide. You can see here Br minus has departed. Okay, now here also you are having K plus and iodine minus. It attacks, bromine departs. Okay, but the difference that you have here, I would rather say the main difference that you have here is of solvent. Look at this. It's a methanol, it's acetone. So you have changed the solvent. Since you have changed the solvent, look at the rate of the reaction. If this reaction is happening in a 1 minute, this reaction is 500 times faster. You're getting my point. This reaction is 500 times faster. The question is why? You must be thinking why it is happening like that, right? The question is obvious. Okay, it should not be that way now, because you can see substrate are same, nucleophiles are also same. Okay, the product, they are also same, leaving groups are also same. The only thing that is changed here is the solvent. So that means, does solvent affects the rate of reaction? Does solvent affects the rate of reaction? Well, yes, it does affects the rate of reaction. We're gonna see how. See, there are two types of solvent: Protic solvent, aprotic solvent. Well, basically, before going to that, we are having two types of solvent as polar solvent, non-polar solvent. Polar solvent are the one which are having dipoles in their molecules, plus charge, minus charge, like that. It could be delta plus, delta minus, like that. Non-polar solvents do not have anything like that. Okay. Now, these polar solvents are categorized as polar protic solvent and polar aprotic solvent. Polar protic solvent and polar aprotic. So, polar protic solvents are what? Polar protic solvent means the solvents where your hydrogen is attached to either of nitrogen, oxygen, or halogen. Whenever you see hydrogen attached to nitrogen, oxygen, or halogen, those type of solvents are called as polar protic solvent. As you can see, methanol. Methanol structure goes like this: CH3OH. Hydrogen is attached to oxygen, so it's a polar protic solvent. And another is what? Another one is acetone. So, is acetone polar protic? Well, acetone is polar solvent. It is a polar because it is having a delta plus and delta minus here. It is having delta plus and delta minus there. But acetone is not protic solvent. Why? Because the hydrogen is attached to carbon, not the oxygen. So now, what does this, how does this plays the role here? Let me show you how. See, your K plus and I minus, what does polar protic solvent does is that they solvates, this polar protic kind of solvents, they solvates both cation as well as anion. Let me show you that in the next slide, because I have kept that empty. Okay, so what did we take? We took K plus and I minus, right? Ultimately, we got that only. Now we had a methanol. What does methanol do? Methanol has CH3OH. We know that hydrogen is having a delta plus here, right? Oxygen is having a delta minus here. So iodine having a negative charge, hydrogen is having a positive charge. So this will start solvating. Okay. Just a second. See, now this is what? This is the solvation. Now from all the side, you will have hydrogen there. See, just like this. Okay. So your basically nucleophile has got solvated. Similarly, your cation K plus would get solvated via oxygen. Why? Because oxygen is having a delta minus charge and K plus is having positive charge. OH CH3, just like that. Now you might ask, so how does it affect? As we know, in SN2 reaction, the rate is decided or dependent on the nucleophile also. And what is nucleophile here? Nucleophile is a negatively charged species. What is a negatively charged species? It's a iodine. So since your iodine is getting solvated from all the side by solvent, it would not find it easier to attack on the delta plus carbon, because now it is being surrounded from all the side by solvent. Firstly, secondly, what does that does? Solvation actually decreases the effect, or I would say intensity of a negative charge that nucleophile has. And if the intensity of a nucleophile decreases, obviously the rate of reaction would naturally get affected. Okay, and that is why if you take Ki in a polar protic solvent, the rate would not be that high. However, when I took acetone, what happens? See, this is the acetone, CH3, C double bond O, CH3. I would rather write here as polar aprotic. So here your carbon is having delta plus, oxygen is having delta minus. Now carbon is having a delta plus, but that delta plus on carbon is not as strong as we had a delta plus on the hydrogen. That is why the carbon cannot solvate anion. However, oxygen, which is having a delta minus, would solvate. It would solvate the cation surely. Basically, from the Ki, the K plus would get solvated from all the side by acetone. It would get solvated from all the side by acetone through oxygen, which will leave I minus, completely free. This would leave I minus completely free. And now iodine minus. In fact, you know what? Polar protic solvent does what? Polar protic solvent helps iodine to get away from the K plus, because polar aprotic solvent is solvating the K plus, which is helping iodine to get away or get free from the K plus, so that it could attack easily or effectively on your substrate. Such thing does not happen in a polar protic solvent. Okay, that is why the rate of reaction increases. In a polar aprotic solvent. I hope this helps you. Okay, so moving ahead. Now, so you now that you understood what is effect of solvent, let's see some of the different kind of solvent. So acetone, as I told you, you have a delta plus here, delta minus here. So these are what? These all are polar aprotic solvent. Carbon delta plus, nitrogen delta minus. Similarly, carbon delta plus, oxygen delta minus. Here also sulfur delta plus, oxygen delta minus. And here also nitrogen having plus charge, oxygen having a negative charge. You can see here phosphorus delta plus, oxygen delta. So all of these solvents, they basically solvates cation, and this sets free. They sets anion free. So that your anion now can attack on your substrate. Okay, sure. Moving ahead. So effect of structure. Now SN2 reaction is not necessarily attacked only by solvent. It is also affected by your structure, the structure of your substrate. See, we already had seen that X does not allow your nucleophile to come and attack easily. This X restricts OH minus from attacking from the front side. Now imagine if it is opposing X minus to attack from the front side, what could be the situation where all three hydrogens are replaced by bulky groups? You can see here, this carbon is having hydrogen, and X. Now your OH minus is coming. X minus is not allowing, so it is attacking from backside, right? That was what happening. Okay. Now in the second species, what has happened? One of the hydrogen has got replaced by what? By bulky methyl group. So now there is a little bit steric hindrance. I'm not saying much, but there's a little bit steric hindrance. Okay. When you go to the next species, which is secondary, this is a primary alkyl halide. This is 0 degree. When you go to primary, so when you go from primary to secondary alkyl halide, so secondary and tertiary. See, primary alkyl halide, only one hydrogen has got replaced by methyl. Secondary alkyl halide, two methyl groups are there, single hydrogen. Tertiary alkyl halide, all the three hydrogens has been replaced by methyl group. Now, where would your OH minus attack? The attack from here was not possible. Now, the attack from here is also not possible. Okay, so basically that is how your substrate should have as less steric hindrance as possible. That is why the rate of attack, or I would say what I should say, rate of not rate of attack, actually the rate of reaction decreases in the order 0 degree, primary, secondary and tertiary. 0 degree, that means methyl reacts fastest, tertiary reacts slowest. Basically, actually tertiary reacts by SN1 mechanism only. It does not react by SN2. That we will see in the next session. Okay, sure. Moving ahead now. So now what is the role of a nucleophile here? See, nucleophile and role, you need to understand. We had seen everything about substrate. Okay, we had seen the effect of solvent. Now we're going to see effect of a nucleophile. See, as you can see here, the rate of SN2 reaction depends on effectiveness of a nucleophile in ejecting the nucleophile. Now basically you should have a leaving group here. Okay, but leaving group again is also nucleophile. Okay, that is why I deliberately wrote nucleophile only there, so that I thought of telling you later on. Okay, so you can see here, nucleophile came, OH minus came, it attacked on carbon, and later on it basically ejected the nucleophile which was present there earlier. So basically one nucleophile replacing the another nucleophile. That's a perfect definition of a substitution, nucleophilic substitution reaction. Okay, actually that's the definition. So now whatever nucleophile comes, how does it play the role? Okay, and you know what, nucleophile could be having a negative charge, could be having a lone pair, but it should have at least a lone pair or a negative charge. Nucleophile, I mean, there is no possibility that nucleophile does not have either of this. It should have either a negative charge or a lone pair. So my question here is that, what's the difference? What's the difference between basicity and nucleophilicity? What's the difference? See, the line between them is very, very fine. Why? Because basicity decides what? Basicity decides your negatively charged species does what? Whether it attacks on carbon or does it abstracts the hydrogen. If you're negatively charged, or I would say a lone pair value species, if it is attacking on a hydrogen, or if it is abstracting a hydrogen, it's surely a base. If it is attacking on electrophilic carbon, then it is what? It's a nucleophile. That's the first thing. Second thing is that basicity is nothing but a thermodynamic consideration, or I would rather say it's a thermodynamic concept, whereas nucleophilicity or attack of nucleophile is a kinetic factor. It's a kinetic factor because it decides the rate of reaction. Now you might say, why not nucleophile abstracts a proton directly? See, we will talk about that as we move ahead, but for the time being, you need to understand one thing here is that for the bases, see, protons are possible. We saw that how nucleophile was not able to attack on carbon. Why? Because from the front side, chlorine or halide group was not allowing it to do so, and from the backhand side, the steric hindrance was there, right? Now, as far as protons are concerned, protons are present on the surface. Protons are present on the surface of the substrate. That is why it becomes easier for the base to abstract those protons. However, for the nucleophile, it is not that easy. Okay, so despite these two differences, many times it becomes quite difficult to identify as to which is nucleophile or which is a base. Okay, so I'm gonna tell you some of the differences and some of the similarities between them, because this point is most important. There have been so many questions asked on this in a previous examinations. Okay, sure. So see, there are two cases. I mean, basically 4 cases. In 2 cases, there is a there's a parallelism. I would say there are some species where there is a parallelicity. You can see nucleophilicity parallels the basicity. Now, nucleophilicity parallels the basicity means what? See, you can see here, negative charge is present on what? Negative charge is present on oxygen. So whenever the species are different but attacking atom, whenever the species are different but attacking atom is same, then always remember that nucleophilicity parallels basicity. That means you need to find out the basicity order. Whatever the basicity order is, same order is applicable for the nucleophilicity also. That is what the meaning of nucleophilicity parallels the basicity. So you can see here, in every case, the oxygen is having a negative charge. So how do you find which is the strongest base here? You have to do simply one thing. You have to put H plus ion. You have to put H plus ion into every species here. And what do you get here? See, F3C, SO3H, Me, SO3H, CH3, COH, PH, OH, H2O, and ETOH. Now we need to find out, see, the strongest acid would always give you weakest base and vice versa. That means weakest acid will give you strongest base. Same thing is applicable when you are going from bases to acid also. Okay, but here we know the strongest acid is this. So if this is the strongest acid, it has to be the weakest base. In fact, if you see all of this, this is the strongest acid here. When you are talking about acidity order here, let me give you an order here. See, when you are talking about acidity order, this has to be the first. This comes second. This comes third. This comes fourth, fifth, and sixth. So this is the strongest acid. ETOH, which is ethanol, is the weakest acid. That means the base formed from ethanol should be the strongest base, and it is the strongest base actually. So this is the strongest base. So this order is of basicity as well as nucleophilicity. Since the nucleophilicity was paralleling the basicity, that means whatever be the order of basicity, same order should be for a nucleophile also when you have attacking atom same. Okay, chalo, let's see some other cases. See here what I have written. Nucleophilicity is anti-parallel to basicity. When you have a nucleophilicity anti-parallel to basicity, whenever the given species, they are present in the same group. You can see here HI, HBr, HCl, HF. All of them are present in a same group. HF, HCl, HBr, and HI. Here, whatever order you get for basicity, the exact opposite order should be there for the nucleophiles. So we know that HI is the strongest acid, HBr, HCl, HF is the weakest. So that's the acidity order. Then what should be your basicity order? Your basicity order should be of F minus, Cl minus, Br minus, and iodine minus. Why do you have this order now? It is obviously that F minus will be having the negative charge. F minus will be having the strength, I would say the intensity of negative charge would be more on fluorine. Why? Because fluorine is small in size. The negative charge is same on all the 4 species, right? Negative charge is same on all the 4 species, but the size is different. Fluorine is smallest in size, iodine is largest in size. So when your atom becomes largest in size, the intensity of the negative charge basically gets spreaded over the larger volume. So density definitely decreases. So when the density decreases, the intensity also decreases. That is why your fluorine would be having the highest electronic density, and hence it would be the strongest base. But that is not the case for a nucleophilicity. For a nucleophilicity, your order should be, and it is reverse. This is the strongest nucleophile. Then you are having Br minus. Then you are having Cl minus. Then you are having F minus. As I already told you the trick, whenever you are talking about the groups which are present in a, whenever you are talking about the species which are present in a same group, you should take the basicity anti-parallel to nucleophilicity. Same goes here. When you are going from NH3 to BiH3, NH3 is the strongest base. So this is the basicity order. Okay, but the nucleophilicity order is exactly opposite. Why? Because all of these groups, they are present in the same group: NH3, PH3, ASH3, SBH3 and BH3. Okay, sure. Moving ahead. Now again, the nucleophilicity parallels the basicity. When they are present, when the species are present in a same period. You can see here, all of these species are present in a same period. You can see here, carbon, CH3 minus, NH2 minus, right? Then you have a OH1 minus, actually. Instead of this, we take a OH minus, and lastly, you have a F minus. Okay, now how do we check the basicity? You just put the H plus sign into this. So when you put the H plus sign, what do you get? CH4, NH3, H2O, and HF. So if I ask you, out of these 4, which is the strongest acid, you will definitely tell me that HF is the strongest acid, and you are right. If the HF is the strongest acid, that means its conjugate base F minus should be the weakest, right? And it is the weakest. Then you are having OH minus, then you are having NH2 minus. We know for sure that methane is surely not an acid. Okay, it is not an acid. But even if you want to measure its acidity, it has to be the weakest. It's the weakest acid that you ever know. Its pKa is 45. You get 45. That means its Ka is 1 into 10 raised to minus 45. It is that weak acid that you can't even consider it as an acid. So if it is that weak acid, that means its a conjugate base has to be the strongest, and it is the strongest. It is the extremely strong conjugate base. And why not? Why not? Okay. So same order is also applicable for the nucleophilicity also. Okay. And that is obviously because carbon would definitely prefer to attack on another carbon. Okay. So whenever you're talking about the groups which are present in a same period, nucleophilicity parallels the basicity. And last, nucleophilicity anti-parallels the basicity. Here I'm going to talk about the bulky groups. What are those bulky groups? Let me give you an example. So CH3OH, This is your methanol. Now let's replace each of the hydrogen. Now let's replace each of the hydrogen by methyl. Okay? Each one of them. Lastly, now if I ask you which is the strongest base, you will definitely tell me that, sir, this is the strongest base. And I won't say you're wrong. You are right. That's the basicity order that you have. That's the basicity order you have. That is right. Why? Because in this OH, you got, see, what does base do? Base donates the electron density so that they could abstract the H plus I. And here CH3 is what? CH3 is electron donating group. Here you got one donating group. Here you got ethyl group. Here you got two electron donating group. Here you got three electron donating group. Three electron donating group would definitely increase the electron density on carbon, which would then increase the electron density on the OH, consequently increasing the basicity. Okay. Now, but you might ask me, so then why the nucleophilicity is anti-parallel here? See beta, nucleophile does what? As I told you earlier, see, if this is a substrate, this is your proton. Protons are present on the surface. Protons are present on the surface of any substrate. So your base can easily abstract the proton from it. Okay. But for a nucleophile, it needs to penetrate. For a nucleophile, it needs to penetrate into the system so that it could attack on carbon. And in the process, it might feel a steric hindrance. Now, I told you how the effect of structure was affecting SN2. So that was only substrate. Imagine if I take this much bulky nucleophile, how would it attack? It will not attack at all because substrate was bulky. Even if you don't take a bulky substrate, nucleophile is bulky now. How would it attack? So it will prefer to do what? It will prefer to abstract the proton from only and it will depart. It will not prefer to attack on carbon, and that is why that is the weakest nucleophile, whereas this is the strongest nucleophile. So I would rather say nucleophilicity order is reverse here for the reason which I told you just now. Okay, I hope you must have enjoyed this. The next part that we're going to see is effect of solvent on nucleophile. Now, before we could check the effect of solvent on nucleophile, you should know there are different types of solvent and what are those. Let's see. Firstly, and you need to know that there are two types of solvent. One is polar solvent, another is non-polar solvent. Okay. Now, in polar solvent also you have a different types. For example, you have a polar protic solvent, you have polar aprotic solvent. Okay. But I'm going to classify this in the one format only. Let's see how. So, firstly, you are having a non-polar solvent. Non-polar solvent, like, for example, you have CCl4 and CS2. What is CS2? CS2 is a carbon disulfide, and CCl4. Both of these are completely non-polar solvent. Then you have a weakly polar aprotic solvent. And weakly polar aprotic solvents are, for example, nitrobenzene. This is the one. Then you have chlorobenzene. Nitrobenzene, you have a chlorobenzene, then you have an acetone. Okay, so these are weakly polar aprotic solvent. The first one was completely non-polar solvent, and third we have a polar protic solvent. Polar protic solvent, and that is your what? That is your water. As we all know, water is polar protic solvent. Now water is polar, that we all know, but it's a protic because hydrogen is attached to oxygen. Okay, now if you check your if you check your nucleophile in either of these or any of these solvent, you would find their nucleophilicity order is, let me show you how is the order. See, suppose you are having this F minus as a nucleophile. These are your nucleophile, for example, F minus, Cl minus, Br minus, and lastly you would have iodine minus. Now these are nucleophile. Now the order shown by these nucleophiles in this solvent would always be, this order would always be this one. Iodine would be most nucleophilic, then Br minus, then Cl minus, and then F minus. Now the question comes, why and how? How the order is in this way only. Okay, now I'm going to decode that. Let's see. See, you do not have a nucleophile directly in this format, right? This must be present in some sort of a salt, right? This must be present in some sort of a salt. What is that salt? This salt must be your, suppose, NaF, NaCl, NaBr, or it could be NaI, right? It could be NaF, NaCl, NaBr, NaI. Now, this NaF or NaCl, NaBr, and NaI, you can take any salt. All those would be existing as Na plus and F minus. Now let me tell you, if you are talking about the very first solvent, this one, this non-polar solvent, they cannot solve it. Non-polar solvent cannot solve it, either a cation or a anion. They are completely non-solvating solvent. So basically I would rather write here non-solvating. Okay, they are completely non-solvating. Now whenever they are non-solvating, that means what? If you put a solvent, if you put a salt, NaF or NaCl or Nab or Nai into this solvent, then what will happen? They would not solvate Na plus, nor they would solvate Cl minus, Br minus, I minus, or F minus for that matter. That means what? That means this salt would remain as a salt only. Okay, this salt would remain as a salt only. Now suppose we take all these anions, F minus, Cl minus, Br minus, and I minus. Okay, they are obviously changing, right? But what's the common? The common factor is Na plus. So what does Na plus do? Na plus would try to decrease. Na plus would try to decrease the effect. The Na plus would try to decrease the effect of an anion, and Na plus would decrease the effect of that anion fastest, which would be slower in size. Why? Sorry, not slower, which will be smallest in size. Why? Because whenever the anion is smaller, the negative charge would be concentrated. Whenever the anion is smaller, the negative charge would be very highly concentrated, and therefore Na plus would be effectively decrease the intensity of an anion which is smallest in size. What does that mean? That means the anion which is largest in size, Na plus cannot decrease its what I should say is intensity. Na plus cannot decrease the intensity of a larger anion that much as it would do for the smaller anion. That means Na plus would be most effectively decrease the effect or intensity of a F minus. And that is why if you take Na plus, or even if you take a K plus, Rb plus any cation for that matter, iodine minus would be iodine minus will be least affected by a cation, and therefore it will be showing the highest or strongest intensity. Therefore, it will be a strongest nucleophile. Okay. Now, so this is done. Now the second part, weakly polar aprotic solvent. Weakly polar aprotic solvent does the same thing. They also does the same thing as it was done by non-polar solvent only. Okay, there is no much difference in that. And lastly, you have is water. Now, what does your water do? We know that water is specially known for its hydrogen bonding. Water is specifically known for its hydrogen bonding. And which anion you think water would hydrogen bond with? Water will mostly hydrogen bond with your F minus. Why? Because fluorine, nitrogen, oxygen, these are the anions with which hydrogen bonding actually happens. Okay, that's the one thing. And we know that water can solvate cation as well as anion. So in this case, water would solvate Na plus, no doubt about that. But when it comes to solvating anion, when it comes to question of solvating anion, the intensity, or I would say the strength with which water solvates is inversely proportional to the size of an anion. That means smaller the anion, the extent with which its solvation happens would be highest. Okay, in other words, F minus would be extensively hydrated by water, because charge to size ratio for the F minus is largest and for the I minus is lowest. So that in other words, the negatively charged intensity is mostly or highly concentrated for F minus, and therefore it is highly or effectively solvated by water. Iodine minus would not be, and therefore the order which I had shown you here would be valid even in a polar protic solvent as water also. And that is how, and that is why the order which I shown you here, I minus, Br minus, Cl minus, F minus is followed, especially in non-polar solvent, weakly polar solvent and polar protic solvent. I hope this must be very much clear with you. Okay, chalo, moving ahead. So, one more thing I was left to tell you, and that thing is, for that I need to clear this. I hope this must have been clear with you. So, I will rub it down. Now, the last solvent that is remain is polar aprotic solvent. Polar aprotic solvent. Now, what are some of the polar aprotic solvent? For example, DMSO, dimethyl sulfoxide. It looks like this: CH3, S, double bond O, CH3. Then you have DMF, dimethyl formamide. How? C, HCO. Just a sec. And CH3 and CH3. Now look at these two solvents. What do you think the solvents would do? These are the solvents which solvates. This solvent solvates only cation. They solvates only and only cation. They solvates only cation, leaving anion completely free and naked, and then your anion would attack as per its intensity. That means, what would your DMSO do? Suppose if I put NaF into this, now what would it do? It would solvate Na plus. Just sec. Yeah, from all the side. DMSO DNS. Now this whole matrix would be like this. Now F minus. Now your F minus, Cl minus, Br minus and your I minus. F minus, Cl minus, Br minus, I minus, they would be completely naked. Now the nucleophilicity order would be parallel with the basicity, or you can say nucleophilicity. See, as I told you, this solvent which I wrote here, this solvent, they do not solvate the they do not solvate the anion at all. They solvate only and only cation. Therefore, anion is completely free. When your anion is completely free, that time the order will be decided by the intensity of an anion. Higher the intensity, stronger will be the nucleophile. You know, between F minus, Cl minus, Br minus, F minus, which has the highest intensity? You know that F minus has the highest intensity, and therefore, especially in polar protic solvent, the order would be this: F minus, Cl minus, Br minus and I minus. Okay, you don't need to remember this. There is a reason for this. Okay, I hope this must have been pretty much clear to you. Okay, so moving ahead now, you can take a look at this. Okay, sure. Now let's see some of the different types of nucleophile and their types. See, nucleophilicity increases as the charge on atom becomes more negative. You can see here, you got the OH minus, neutral water and H3O plus. Higher the negative charge, more will be the nucleophilicity. This is the negative charge, this is neutral, positive charge. So the order should have been like this only. Okay. Secondly, nucleophilicity increases as the basicity. This we had already seen. CH3 minus, if we convert it into its conjugate acid, it will be CH4, NH3, water and HF, right? And out of these four, which is the weakest acid? The weakest acid is methane. So since methane is the weakest acid, its conjugate base CH3 minus is the strongest, and that is why the nucleophilicity order here. And lastly, nucleophilicity increases with the polarizability size. We know that as we go down the group, the nucleophilicity always increases because polarizability also increases, which we had seen before also. Okay, I just wanted to highlight here also, so I put it, I brought it again. Okay, and here also you can see this order, right? Okay, I hope this have been pretty much clear to you. Now moving ahead to our last point, and that is leaving group or fugacity order. Leaving group or fugacity order. Now don't get carried away by what is this fugacity order. Fugacity order is nothing but a leaving group ability. And what decides your leaving group ability? Leaving group ability, or I would rather say fugacity order, is directly proportional to the, I would rather say inversely proportional to the strength of a base. Strength of a base. Weaker the base, stronger is its leaving group ability. It is that easy. That means whatever leaving group is departing, obviously leaving group also holding a negative charge, right? Now negative charge means what? We consider it as a base. Okay, so if it's a weaker base, then it's a good leaving group. It is that simple. So as I told here, as I written already here, leaving group ability, your leaving group ability is inversely proportional to basicity, or you can say leaving group ability is directly proportional to conjugate acid strength. So whatever leaving group you have, just put H plus ion into it, you would get the acid. If that acid is stronger, that means the anion which was earlier, the anion which was there before you put the H plus ion, is the good leaving group. Okay, let's see or understand it through the example. Okay, see, HCO minus, this is format acetate ion, then you have what, your benzoic acid, and then you have chlorosulfonate acid. Now what I'm going to do, I'm going to put H plus ion into all of this, and let's see what acid do I get. H plus ion, H plus ion into this, H plus ion into this, and H plus ion into this. Okay, now let's see what I get. I get is HCOH, formic acid. Here I get acetic acid, right? Here I would get benzoic acid, and here I would get Cl3 CSO3H. Now we know this much, we have surely studied that this is the strongest acid here. Now if this is the strongest acid, its conjugate base has to be the weakest. So if its conjugate base has to be the weakest, it has to be your most good living group in this 4 example. Okay, if you look at all these examples, you would know that in this is the strongest acid. Second one would be this. This is your second one. This is your first one, right? This is your second one. Then among acetic acid and benzoic acid, the one which is more stronger is what? Is a benzoic acid. This is third one, and this is the fourth one. So this is the strength of your acid. So just flip it back. Just flip it back. You would get the living group order. Living group ability order. You can see here, this is the strongest acid. So its conjugate base has to be the weakest, and therefore this has to be the most good living group. Then second number would be this. This is the strongest acid. It's a second number strongest acid. Its conjugate base would be second number. This is your second number. Among these, the picture is quite clear. This is your third number, and this is your fourth number. Basically, acetate ion is the acetate ion is the worst living group in this 4. Okay, it is that simple. Now look at this 4. Now here the picture is very, very easy. How the picture is very, very easy? Let me tell you. See, as soon as you put H plus ion in all of this, as soon as you put, just a sec, H plus ion into all of this, what do you get? You get HF, HCl, HBr, and HI. You know which is the strongest acid here, right? HI is the strongest acid. If the HI is the strongest acid, that means what? I minus is the weakest base. If the I minus is the weakest base, therefore it should be the strongest or very good living group, and F minus is the weakest living group. Therefore living group ability order here goes like this. Or you can understand to simple example that whatever examples have been given to you, just look at how effectively it dissipates that negative charge. The extent with which it is dissipating the negative charge overall the complete species will make it good living group. It is that simple. Okay, so I hope you must have understood lots of concepts here. That's the complete rapid. I'll wrap it here. This is the complete SN2 reaction mechanism. Okay, many of these facts will also helpful for you in understanding SN1 mechanism also. Okay, but that's it for the SN2 mechanism. Now one more thing I wanted to highlight to here is that, have you observed that iodine I minus, this I minus is just this I minus is a good living group as well as a good nucleophile. Okay, that's it for this today's session. I hope this is helpful for you. In the next session, I'll be coming up with the SN1 reaction mechanism. Thank you.
Bring learning alive practically.